This video is produced by Sammy and
Kevin Burgess
for byinquisition Press to support the workbook Sophomore Organic Chemistry 2 by Inquisition, available from www.byinquisition.org.
Are you ready, Sammy? Off we go. In the last video, we talked about reductions of polar bonds by hydride. There's another way to reduce polar bonds and actually apolar bonds too, and that's by adding not 2 electrons, but 1 electron in a radical process. For instance, if I take a aldehyde and add 1 electron to it, we've got to remember to push fishhook arrows, and that generates not an anion, but a radical anion. Ketone will be reduced to the corresponding radical anion of the ketone. Similarly, for an ester or an amide, we get the corresponding radical anion. Let's suppose we generated a radical anion by adding an electron to what, Sammy?
The alkyne.
Yeah, an alkyne. That would be but2-ine. And then protonate it, we would get a radical. We protonate the anion part and leave the radical part behind. This radical anion is formed from a ketone. And if I protonate it, I will get a radical carbon-centered protonated on the oxygen. Let's suppose also that we take a radical and then add another electron to it. Well, the electron brings 1 charge with it. So if I take this radical that we formed by protonation of the radical anion that we got from a ketone, then I will form an alcohol. If we were to put in our but2-ine and add an electron, that would add nicely and give us a radical anion, but ammonia is acidic enough to protonate the radical anion on the anion part, leaving a radical. But that radical is reactive enough to react with another electron to form an anion, which can be protonated again by the ammonia to give a product. So in 2 1-electron steps, liquid ammonia with sodium in it can reduce but2-ine to give us an alkene. The reason it's trans is because the anion intermediates and the radical intermediates can equilibrate. Benzene is also reduced, and that's a particularly interesting reaction. Addition of an electron to benzene gives a radical anion, but the radical and the anion repel each other. So fortunately, by resonance, either the radical or the anion actually could move, and the most stable state is to put the radical and the anion parallel to each other. Protonation of that radical anion by ammonia will give a radical, which can be reduced again, and then protonated to give the reduced product. The reason the 2 double bonds are not conjugated with each other is because the radical and the anion resonated to be as far apart as possible. If the benzene was substituted, then in the case of 1,4-dimethylbenzene, there would be 2 possible radical anions. The one that has methyl substitution on the radical and on the anion is actually the least stable. More substituted carbanions are more alkyl substituted carbanions, more or less stable than non-substituted ones.
They're less stable.
Less stable. Are more alkyl substituted radicals more or less stable than non-substituted ones?
They're more stable.
They're more stable. But actually, it's the anion that takes precedence here. You look at the anion stability. So we don't form tertiary carbanions. Organotin hydrides are a very good way to generate radicals. The tin hydrogen bond is not very strong, and tin radicals are quite stable. So they tend to undergo homolytic fission to give a hydride and a tin radical. Tin radicals can abstract iodine radicals from alkyl iodides or from aryl iodides actually, giving alkyl radicals which can be quenched by a hydrogen from another tin hydride species. Let's look at reduction of an aryl iodide. The initiation step is generation of hydrogen radical and tin radicals. In the propagation step, it's the tin that abstracts the iodide to give an aryl radical and quench it with another hydrogen donor to give the product. If two radicals come together, that's a homolytic fusion if they're the same. And we take radicals from the system, that's a means of terminating the reaction. A beautiful example of radical chemistry in biosynthesis is generation of an oxygen-centered radical in prostaglandin synthesis. That abstracts a hydrogen atom and generates an allylic radical that of course can move by resonance. It reacts with oxygen to give, after cyclization, an alkyl radical, but that cyclizes too to generate a carbocyclic ring. Finally, the radical produced is quenched with dioxygen, and after a further reduction, prostaglandin H2. Is vitamin C good for you?
Yes.
And one of the reasons it's good for you is it removes reactive oxygen species. Are reactive oxygen species good for your cells?
No.
Your cells hate them. Yeah, your cells will be oxidized just like they would if you put bleach on them. Reactive oxygen species are actually formed by reduction of oxygen. So if I add a radical to dioxygen, I get superoxide, which is a radical anion. If I add an electron to that, then I would get peroxide anion. If I take peroxide dianion and add 2 protons, I would get hydrogen peroxide. And if I add 1 proton to the superoxide radical anion, I would get a per-hydroxyl radical. And all these things are bad for you. That's why you should take your vitamin C.